Start with line graphs, and let's say we're scanning some photographs and they're charged a $25 setup fee for the scanner and then 55 cents per scan. And how much would they get charged for 8 scans, and how much would they get charged for 15 scans? Well, we can do the math on this, and we have, giant pen, make it a more reasonable pen. $25 plus 8 times 0.55, which would give us the 8 scans at 55 cents, which would be how much? Yes. So 8 would be $4.40, so that would be $29.40. And then if we're doing 15 scans, we'd have the 25 plus 15 times 0.55, which is $8.25, giving us $33.25. And then if we wanted to find 100 scans or 200 scans, we could do the same process, but it can be really time consuming if somebody's standing there in line and saying, well, how much for this many scans? Well, how much for that many scans? How much for this many? How much for that? If we had a graphical representation of that, it would be really easy for us to just see how much per scan. And then we can go, oh, that would be this much, that would be that much, that would be this much. Instead of saying, okay, hold on, every time. So we're going to explore the concept graphically. We need to talk about things that, mostly you guys already know. Variable. A variable is a letter, generally, sometimes another symbol used to represent an unknown quantity. So any number we don't know, that's a W, not a U, can be represented by a variable. A data set, and a data set is just that. It's a set of data. Typically we're talking about numbers, but we can be talking about other types of data. There is non-numerical data. Usually that is called qualitative data, and numerical data is quantitative. And we can have either single values, or we can have, paired values. For example, our X and Y coordinate pairs, etc. Okay, quantitative data is numerical. Quantitative for quantity. And quantitative can be discrete or continuous. Okay. And we talked about that in term A, discrete variables being individual data points. Where we have no run-on, no data point runs into another data point. Usually we talk about this as being integers or set fractions. Not that I can have any kind of fraction, but I can only have halves, or I can only have thirds. So I could have 1, 1 and a third, 1 and 2/3, 2, something like that. Continuous variables are data points that can run into each other. So it's data that sort of bleeds into each other. Okay, things that we can think about that would be discrete variables. Number of cars in the parking lot. You have 1 car, you have 2 cars. You don't have 1.67532 cars, right? You have just, it's a car or it's not a car. No, we don't. Same people, right? You cannot have half a person. You have a person, or you have two people, or you have no people, but you don't have 0.25 of a person. Unless you're Dexter. But we're not Dexter, so we can't have 0.25 of a person, right? So these are discrete variables, things that are like you have it or you don't. There's nothing in between. They're not running into each other. Continuous variables are things that run into each other. Growth. Growth is continuous variable because we don't wake up, this morning we're 5'1", and we go to bed, and tomorrow morning we're 5'3", and you just instantly went from, like in an instant, went from 5'1" to 5'3". You went through all the parts of inches between 5'1" and 5'3", right? So growth is a continuous variable. Volume. If I'm filling up a bucket, it's not empty and then instantly full. It gradually fills up, and so the volume is continuous. Things like that, things that will run into each other are continuous variables. And then we have qualitative data, which is non-numerical. And qualitative data does not count as discrete or continuous because we're not talking about numbers. Qualitative data is about the, it's called qualitative because it's about the quality of things or characteristics of things. In statistics, you don't do a lot with qualitative data. Usually statisticians try to assign numerical values to qualitative data to make it mathematically analyzable. That's even a word. But qualitative data would be color, flavors, textures, feelings. In the social sciences, you get a lot of qualitative data, motivations, perceptions, things like that. So those are your qualitative data. We would be mostly dealing with things like colors. When we talked about probabilities and we talked about a bag of marbles and we had different colors of marbles, the number of the different colors of marbles would be the quantitative marble data, and the different colors would be the qualitative marble data. Okay. So here we have a graphic. We have variables, and they can be either quantitative or qualitative. If they're quantitative, they can be discrete or continuous, and we can have dependent and independent. Okay, the independent variable is the variable that can be chosen or that we have no control over. For example, like time. Time is going to pass. There's nothing we can do about it. Or variables that we can choose. If we're talking about how much grapes cost, we can choose how many pounds of grapes we're buying, right? So that's the independent variable. And then the dependent variable depends on the value of the independent variable. So for example, in the grapes example, the independent variable would be the number of pounds that we chose to buy, and then the dependent variable would be how much the grapes cost. So it's sometimes easier to identify the dependent variable than it is to identify, like straightforward, identify the independent variable. You just look at your two categories and you say which one of these depends on the other one. And then you've identified your dependent variable, and then the other one is independent. Does that make sense? Okay. Please. Number of people in a family. Quantitative or qualitative? Okay. Discrete or continuous? No, discrete, because I can only have individual people, right? My people don't bleed into each other. This is not human centipede. I'm just saying individual people. I've never seen it. It just, ugh. Okay, so discrete. Okay, person's marital status. Married, single, divorced, widowed. Qualitative. And since it's a qualitative, it can't be discrete or continuous. It's neither. Okay. Length of your arm. Quantitative. Discrete or continuous? Continuous, because you can have all the different fractions of inches and lengths of arms, and as you grew, your arm grew gradually and the length flowed into itself. Okay, color of cars. Qualitative. Number of errors on a math test. Quantitative. Discrete or continuous? Discrete. Okay, good job. All right, so Sally works for the local ballpark and she sells lemonade. And she is paid $15 each time she works, plus 75 cents for each glass of lemonade she sells. So we are going to create a table of values and then we're going to graph it. So basically, if we were doing an equation, she's going to have $15 is her flat fee, and she's going to have 75 cents per glass of lemonade. So if she comes to work and she sells no lemonade, she still makes $15. Okay. And if she sells one glass of lemonade, she makes $15.75. And if she sells 2 glasses of lemonade, she makes $16.50. And if she sells 3 glasses of lemonade, she makes $17.25. 4 glasses of lemonade, and she makes $18. Okay. So we're going to go ahead and graph because we have more than enough points to graph it. Our independent variable is the number of glasses of lemonade that she sells. She really has no control over that, right? People are going to either come buy the lemonade or they're not. So that's our X value. So they've got 1 glass, 2 glasses, 3 glasses, 4 glasses, etc. And I'm going to go ahead and start my Y at 15 because I don't have any values less than 15. And then I'm going to go up by a quarter each time, since I'm dealing with 75 cents. So far, okay? Okay, so if she sells no glasses of lemonade, she's at $15. If she sells 1 glass of lemonade, she's at $15.75. 2 glasses of lemonade bring her up to $16.50, so $16.25.50. 3 glasses of lemonade. Wait, did I go up enough? Hold on. 15.75, 16, 16.20. Yeah, one more up. Yep. And the pattern is known as what? Oh, come on, you guys remember this rise over run? Slope. Pattern is known as the slope. So if I graph this line, the slope is 4. And to figure out how much money she's going to make, if she sells 8 glasses, I don't think my graph went far enough. It did not. Oh no. 1, 2, 3, 4. We need 4 more spots. Okay, well, we'll go ahead and just plug in 8. And 0.75 times 8 is 6. So that would be $21. Okay, let's talk about scale when we're graphing this. Now our X value goes from 0 to 6. If we use just the individual lines, that would be 1, 2, 3, 4, 5, 6. Our entire graph is only going to be in this tiny little space. When you're graphing, to make things look the most visually accessible, you want to take as much of the space as you can. So instead of making each line worth 1, I can scale this out by making each line worth 2, and that would bring my graph out this far. Or I could make it by 3, and it would bring my graph out this far. Or 4s. You see I'm stretching the graph out? So I'm going to go by 4s, and I'm going to say every 4th square is 1. 2, 3, 4, 5, and 6. And I did that because I know that there's a maximum of 6 hours. So I'm not going to have to look at any data past 6. Right, this ends at 6 hours. It's like a skate-a-thon, and it's got a set time. Now my values on my money is between $10 and $28. I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I lost my place. Okay, so I've got like 30 or so spaces, and I need 18. So I can either test my luck and go by 2s because I didn't finish counting, or I can just go by 1s. I am starting with 10, but I've got 18 spaces between 10 and 28. Yeah, so I'm going to go by 1s, and I'm going to call this 10, and that would be 11, 12, 13, etc. So if I don't skate, I just go and I pay the $10 for registering because I believe in the scoliosis charity and I want to help, but I don't skate. I raised $10 for them. Okay. If I skate for 1 hour, $13. 2 hours is $16. 3 hours, 4 hours, 5 hours, and then 6 hours. Okay, now this line, pretend is straight, is not going to have an arrow. Because 6 is the maximum, this line is going to end. So we're not going to put an arrow on it like we do normally. Okay, and that's going to be kind of a difference between the lines that we graph here and the lines that we graph in algebra. In algebra, lines are continuous for infinitely, and so they'll continue forever. But when you're talking about hard statistics, real-world data, there's not an infinite number of money that can be raised for this charity. We're not going to get that high. But one person is not going to raise infinite money. So there will be a limit, and the graphs will end. Let's say somebody skates for 3.5 hours. Well, then they would have raised, what is that, 19 and 22? They would have raised like 20.50. So we could, if we had our scale over here, or actually these are in even dollars. So let me find it real quick. Oops, right here. So 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. $20. Okay? So we can find all kinds of things like that. Good? All right. Next. Broken line graphs, okay? Remember we have the videos on page 250. And broken line graphs are graphs with starts and stops. You can think of it that way. There's starts and stops. And it's like this. So we're driving to a family member's house, and it's 20 miles away. And so We travel at 55 miles per hour. Then we get there and we have dinner and we socialize. How fast are we traveling at that point? 0. And then we drive from there to the store and pick up groceries. And we slow down because we're lost. And we drive 28 miles per hour. And then we drive 15 miles in the direction. So when we graph all this, yeah, we're going to have a lot. So we're going to have, depending on how we do the scale, are we talking distance? Are we looking at time? Are we looking at speed? Okay. Right, well, we probably would do distance and time. Okay, and so when we first start traveling, we're going 55 miles an hour, making, going up in distance, and then we stop. And time is passing, but the distance is not changing. Then we go to the store, and we're getting closer to home, but we're going slower, so it's not as steep. Pretend it's a straight line. Then we go to the grocery store. And then we talk to the clerk. Then we drive home. So it's lumpy. It's not nice straight lines. It's like mountains and plateaus and things, okay? So a broken line graph is a graph with, you can have actual breaks. You can have plateaus. You can have peaks. Basically, you're not a straight line. We have a broken line graph, distance and time. We're talking about from 0 to 8 hours, and we have the distance from 0 to 20 miles. What is the fastest speed of the bus? Well, we look for the steepest line. Here I'm going up 4 and over 1. And here I'm going down 1, 2, 3, 4, 5, 6, 7, 8 and over 1, basically. So this slope is steeper than this slope. So the fastest speed of the bus is between 5.5 and 6.5 hours. And during that time, we went 16 miles. Still slow, but it was the fastest that bus went. Okay. How many times did the bus stop? 4. Says don't count the beginning and end. Oh, yeah, 4. 1, 2, 3, 4. 4 stops. What is the initial distance of the bus from the bus depot? The initial distance. How far? If 0 is the bus depot. Right, so we're 2 miles. And what is the total distance traveled by the bus? We go from 2 to 20, which is 18. And then from 20 to 0, which is 20. So 18 out and 20 back, so 38 miles. He's spending time with his friend Aaron, and they go on a bike, and he's going to Aaron's house, but he gets a flat tire, and he has to walk the remaining distance. Ugh. Then they play some poker, and Sam comes home, but he stops in the mall. So if we look at this, okay, here's his initial traveling. He's going fast, right, because he's on a bike. Yeah. Then he has to walk his bike because he gets the flat tire. Then they fix the tire and he plays poker. Then he goes home. He's traveling fast again, but he goes to the mall, and then he's home. Okay? So how far is it from Sam's house to Aaron's house? Sam's house, here's where he gets at Aaron's house. So 25 miles. Okay. How far from Aaron's house to the mall? We've got 25 minus 10. Yeah. Oh, you're right. Thank you. Well, that makes it much shorter. And see, here I was all thinking that Sam was pretty buff. Right? Okay. What time did he have a flat tire? 10. Right? 10 o'clock, because that's when he slowed down. No, yeah, time. How long did he stay at Aaron's house? Yeah, we're from here to here, so about an hour. And what speed did he travel from Aaron's house to the mall, and then from the mall to home? Okay, so here's Aaron's house to the mall, right? Aaron's house to the mall. We have gone, let's see, 25 to 10, so 15 kilometers. Okay, and we did that in 30 minutes. So that would be 30 kilometers per hour. So far, okay? And then from the mall to his house, he went 10 kilometers in 15 minutes. So that would be 40 kilometers per hour. Yeah. Okay. So any questions about this one? It's good? Okay. Guys, I want you to do this one for me. Oops. I want you guys to make up a story to go with this graph, and then we'll share the stories.